All right, it's 11 o'clock, so good morning, everyone. This is the February PAC Fellowship Seminar. We do these once a month for anybody who would like to attend, and specifically members of the PAC Fellowship. This month's speaker is Dr. Susan Trolier-McKinstry, and she's a professor of ceramic science and engineering at the Pennsylvania State University. So she is going to give a presentation on thin films for piezoelectric microelectromechanical systems. And I'm going to turn it over to you, Dr. McKinstry.
Good morning or good afternoon to everyone who is listening. Let me encourage you that this will probably be more engaging if there's the possibility of questions. And so I have a chat screen open. So if anyone wants to send questions by chat, that would be great. If not, please go ahead and just ask them verbally. So I will say a few words about some of the work that my group does on thin films for piezoelectric microelectromechanical systems. There are many, many people that have contributed to the work that I'm showing today, from Penn State, the Smithsonian Astrophysical Observatory, IBM, North Carolina State University, University of Glasgow, IIT, Bangalore, and the US Army Research Lab. So most of you are carrying around with you piezoelectric thin films in microelectromechanical systems. And these are the aluminum nitride or the aluminum scandium nitride thin films that are used in the resonators that do the frequency filtering in your cellular telephone. And historically, the devices that did this frequency filtering were dielectric resonators. They were about half the size of your smallest finger. And a number of years ago, those were completely replaced with aluminum nitride, aluminum scandium nitride, or your favorite piezoelectric film, usually in a suspended structure. And this vibrates in the thickness mode. And because all materials, which are piezoelectric, convert between electrical and mechanical energies, there's always some, as I undergo a mechanical resonance, there's always an electrical signature of that mechanical resonance, and we use those changes in the electrical impedance to make extremely small resonators. And so I show in this corner of the screen that I'm circling a thin film bulk acoustic resonator that's based on aluminum nitride. You can see the dimensions are more than an order of magnitude smaller than the dimensions of the device that it replaced, the dielectric resonator. And as a result, we now have many tens of these frequency filtering devices in a modern cell phone because of the large number of communications channels that we utilize. The key figure of merit for this application is the coupling coefficient K squared times the mechanical quality factor of the resonator. Materials like aluminum nitride or aluminum scandium nitride have really very modest coupling coefficients due to their modest piezoelectric responses. But because there are almost no mechanisms for mechanical loss in those material, the coupling coefficients are really quite high. And the net result is that materials like aluminum scandium nitride are currently the gold standard in this application. Unfortunately, however, the piezoelectric coefficients of those materials really are very modest. And we can see that if we think about the key piezoelectric coefficients for a microelectromechanical system, one of the characteristic features of those systems is they tend to utilize thin films. And most piezoelectric materials will strain limit between 0.1 and 1%. And so if I only have a thin film that's a micron thick, I don't get much absolute displacement from that film unless I use a mechanical amplification system. So we tend to make benders out of these devices And for a bender, the key piezoelectric coefficient is the E31F coefficient, which relates the in-plane strain to the out-of-plane dielectric displacement, or we can also relate the out-of-plane electric field that I apply to the generated in-plane stress that acts to bend the structure. And in a sensor, the key figure of merit for a voltage-based sensor is this E31 coefficient divided by the relative permittivity. If we use a charge-based sensor, it's simply E31F. For actuators, I need a large E31F. For piezoelectronic transistors, which we have time will be the last topic I'll discuss today, we actually unusually use a rather different coefficient where we use the out-of-plane D33 coefficient in the MEMS structure. And finally, for an energy harvesting system, the key figure of merit is really the product of E times the H coefficient. So what I'm going to try to do as we go through this presentation is to give you a few examples of where use of a material like lead zirconate titanate, which has a very high piezoelectric coefficient E31F, where that can be useful in piezoelectric microelectromechanical systems. I'll talk about it from the standpoint of adjustable optics, micromachined ultrasound transducers, energy harvesting systems, and if we have time, post-CMOS transistors. So let's begin with the energy harvesting scenario. So if I look at the ambient mechanical energy that might be available for energy harvesting, most of it is at low frequencies, often less than 100 hertz. And if I'm going to make a thin film device, which is inherently only a few microns in dimension in the thickness direction, if I want to be able to match the resonating frequency of that structure to the available mechanical energy, I tend to use devices which are very thin, they're comparatively long, they have heavy weights on the ends of them, and often we will use top and bottom electrodes. In that case, the power that I can generate from such a system will scale with the square of the strain that I can generate, the volume of the piezoelectric, and the E31 coefficient squared divided by the relative permittivity. And so if you look at materials like lead zirconate titanate has outstanding piezoelectric coefficients, typically on order -12 coulombs per meter square, but also very high permittivities when we grow those films on silicon. The net result is that I get this figure of merit of about 0.12 coulombs squared per meter to the fourth. Aluminum nitride, which as I said is really a very modest set of piezoelectric coefficients, nonetheless has a relative permittivity that's 100 times smaller, and the figure of merit on silicon is essentially identical to what we would have for a much better piezoelectric. And so I was very interested in understanding whether we could do better than that. And if you look at the available calculations say if I can take lead zirconate titanate and arrange it so that all the polarization is out of the plane of the film, that gives me the maximum E31 coefficient and the smallest relative permittivity, the best available combination of coefficients for this energy harvesting application. And phenomenology says I should be able to move from this value of 0.1 coulombs squared per meter to the fourth up an order of magnitude. And that's certainly very interesting from an energy harvesting perspective. And so we worked on building thin films which would have polarization that was pointed out of the plane. The way we did that, since the films need to be thick and epitaxial constraints will relax at the relevant thicknesses, we use the thermal expansion coefficient difference to provide the required in-plane compressive stress to force the polarization out of the plane. And when we really do force all the polarization out of the plane, we get a figure of merit for energy harvesting that is very appealing. It's the full order of magnitude improvement that we hoped for. Unfortunately, The substrates on which we first explored this high figure of merit were all single crystal oxide or fluoride substrates, which are incredibly difficult to micromachine. And so practically, it was incredibly hard to make devices that function. They tended to fracture the very first time we strained them. And so we needed as a group to be able to switch to an alternative substrate that would be mechanically more robust, but which would also allow us to generate substantial levels of compressive strain in the ferroelectric film. And the way we did this was to use base metal foils. We've now done this on nickel and stainless steel. There's not a whole lot of difference between them. We start with our metal foil. We grow a layer of hafnium oxide by atomic layer deposition to prevent or at least reduce subsequent oxidation of the metal foil. We then grow on top of that lanthanum nickel oxide, which is an orienting bottom electrode. And then we can grow either by chemical solution deposition or sputtering thick lead zirconate titanate films that are under a reasonable value of compressive stress and have figure of merits on order 0.4 coulombs square per meter to the fourth. And one of the real advantages of using the metal foil substrates is that they're now very flexible. We can impose large in-plane strains in the material in order to generate large outputs. What you're seeing here is a compliant mechanism design. You can see two hinges very clearly here. There's an additional hinge at this point. Those act to help us bow the nickel foil, which has several microns of lead zirconate titanate on both sides, into an approximately parabolic shape that provides better uniformity of the strain than a typical cantilever will. And that allows us to get much, much higher levels of power output than has been previously reported for most other microelectromechanical systems for energy harvesting. This shows data for some resonant harvesters. We've also looked at some non-resonant harvesters, which utilize an eccentric rotor, which has magnets embedded in it in order to pluck a series of piezoelectric beams. And you can see the operation of one of these devices here. So here's an energy harvester on a wrist. And as one of the magnets moves past the magnets on the end of the piezoelectric beam, we can force the piezoelectric beam into mechanical vibration and then scavenge the energy based on that. Our projections for a device in which all the beams are operating is that we should be able to achieve about 140 microwatts based on devices that have a limited number of working beams. And that power output can be generated during walking by the human wrist. The second topic I'm going to say a few words about is the use of piezoelectric devices for adjustable optics. Our motivation here is for adjustable optics for the proposed LYNX X-ray space telescope. This is an X-ray telescope. You focus X-rays on reflection from curved surfaces. So you can see here a whole series of piezoelectric coated glass shells that would then be used. They have a very precise shape in two different dimensions, and they're used to focus the X-rays. The hope is that we'll be able to use this telescope to probe our understanding of the very early universe. If you look at the projected size of this telescope, they're interested in being able to have several hundred to maybe as many as 10,000 square meters of adjustable optic. And as you do so, you should be able to very precisely control the side of the shape of this curved piece of glass. So what we do is put an array of actuators on the back of this curved glass. And Alexi, I see your note that you can't hear anything. My microphone is showing as projecting. So if you could possibly just double check your speaker connection, please and thank you. So we learned how to put piezoelectric films on the back of glass substrates. And what I'm showing here, not very successfully, is a set of basically the change in the surface figure. I'll move on so that we can see it in a subsequent slide. But basically what we've been able to do is to be able to grow piezoelectric devices on the back side of these mirrors. And we've been able to mount them in flight-like mounts. And so you see here a chrome iridium film that's intended to reflect the X-rays. If you look carefully, you can see a whole array of piezoelectric actuators on the other side of these devices. And this shows that even in a university laboratory, we're able to achieve 100% yield on centimeter square electrodes. And what you're watching, that pattern that you're watching moving across the screen, is the deformation that's introduced as we actuate each one of those lead zirconate titanate pixels independently. We've demonstrated that if we design this appropriately, we should be able to achieve about a 0.3 arc second angular or arc second resolution, which will completely meet the specifications for the proposed Lynx X-ray telescope. But we now have a fairly complicated controls problem. So we have actuators either every centimeter square or every quarter centimeter square for hundreds of square meters of shaped glass. And I need for every actuator one continuous bottom electrode and one top electrode for every single one. So if we have simply 40 by 40 contacts, that means we need 1,601 individual electrical connections. If, however, we can put on the device a thin film transistor such that we have a basically a transistor that will do voltage hold on the device, we can reduce the number of required contacts from 1,600 for every sheet to 800. And that meant we needed to learn how to deposit lead zirconate titanate as our actuator, and then on top of that, thin film transistors. And our approach has been to use zinc oxide thin film transistors arrays. This is done courtesy of collaboration with Professor Tom Jackson in the Electrical Engineering Department at Penn State. We do the thin film transistors by a plasma enhanced atomic layer deposition of the zinc oxide and also the gate dielectric. The entire thin film process is done at 200 degrees C, which is well below the process temperatures for the lead zirconate titanate. And this allows us to successfully put thin film transistors. And we've recently completed a device where we've demonstrated that we can do voltage control of the thin film of the piezoelectric elements with these thin film transistors. And we're working now on being able to do a flight test of this in a rocket launch. And so you can see here one of our very early generation devices. So this is centimeter square electrodes. Here's the thin film transistors. Very tragically, this device was broken partway through the measurement. So we don't have great data, but you can see that we are able to move the deformation pattern across the device, across the substrate, using these thin film transistors. The next topic I'd like to discuss is some work that we're doing on piezoelectric micromachined ultrasound transducers. Many of you are familiar with medical ultrasound. It is the second most widely used imaging modality in the medical realm after X-rays. And it's the only form of medical imaging that's inexpensive enough to have in every doctor's office. These devices are the ones you find in a current doctor's office are piezoelectric bulk materials, which have been subdivided into individual elements by diamond sawing. Typically, those devices are actuated at 60 to 100 volts. And it would be very, very useful to be able to decrease the operating voltage of these devices by simply decreasing the thickness of the functional piezoelectric. That allows us to get large absolute electric fields at small absolute voltages. And so we make devices which use some passive elastic layer and a piezoelectric layer on top with its top and bottom electrodes. And then this bends very much like a drum head. The way we make these devices is shown here. We start with a silicon on insulator wafer, which we passivate the top surface of. Then we grow the bottom electrode, a layer of lead zirconate titanate as our piezoelectric. And then we pattern the top electrode. And finally, we come through and remove some of the back of the silicon wafer using a deep reactive ion etch process to make the membrane structures. We then dice it into individual die and coat the wire bonded structure with perylene so that the entire structure is waterproof. You can see one of the individual die here where the active elements in this case are about 50 to 60 micron diameter diaphragms separated by 75 microns. We are able to generate adequate levels of sound pressure in order to be able to do imaging from these devices. And the exciting thing is that they can be actuated at only a few volts. When my student started to do the imaging, he had no idea whether it would work, so he made some model targets. So you see here a heart and a broken heart, and he didn't know whether the experiment was going to work, so he imaged it, and he shows us the heart because this is the ultrasound image made by actuating one row of those diaphragm elements and then stepping that progressively across the device. And you can see that we're able to get relatively good resolution imaging of those parts. We've also, and we've demonstrated now photoacoustic imaging as well. We've also done some work where we're trying to learn to control particles that are suspended in fluids above these transducers. What you see here is calculations of the pressure field that's generated by two adjacent transducers. You can see that those pressure fields overlap somewhat. And the net result is that if you use particles that are suspended above the transducer in a fluid medium, we generate adequate levels of acoustic radiation forces that we can force those particles to congregate. And so we've been able to generate images where we can move particles back and forth over these devices. So what you see here is 4 individual transducer element, and we're marking whether or not we have the voltage on or off. This haze that you see above is a series of 4 micron diameter silica beads in distilled water. And you see that as we turn the voltage on and off, we are able to selectively move particles suspended in the fluid above the transducer. We're able to move them left and right, and we're able to do this in a deterministic way. And we believe that this will allow us ultimately to do things like particle separation for example, perhaps the constituents of a biological sample may be very useful for separating, for example, one type of blood cell from another simply based on the size and the acoustic properties of those particles. And then I have 5 minutes left, so I'm going to very, very rapidly talk about the most futuristic program that we've been working on, which is to replace silicon as a transistor. Many of you are familiar with the fact that there's been enormous levels of progress in the scaling of numbers of transistors by downscaling the dimensions of those transistors. What I had not appreciated is that clock speed of those devices saturated or came close to saturating close to 2003. And that was really a choice we made based on power. So as we scale devices down in size, in principle, we could speed them up. But we choose not to because the on-off ratio degrades unless we use large voltage swings. That's a fundamental consequence of the 60 millivolt per decade turn on of the silicon transistor. And so if we want to keep that voltage constant, so we can basically keep the chip power largely constant, we've actually chosen in some cases to downclock the silicon transistor. If we really want to change this, we need to change the fundamental physics of the device, which is our transistor. And so IBM came to me a number of years ago and said, just suppose we could make a piezoelectric material that I've shown as PE here, and we could use that to compress a piezoresistor. So as I apply a voltage, this piezoelectric is going to expand in its thickness direction and contract laterally. And if it expands enough, I can compress a piezoresistor against a stiff surrounding material. And their prediction said is that if you could get the properties of known bulk materials and you appropriately scaled them, you should be able to make a piezoelectronic transistor that operates at lower switching energies and higher clock frequencies than FinFETs, carbon nanotube devices, or tunnel FET devices. And that was really appealing. And so we decided to try to see whether we could fabricate such devices. The approach we took was to use magnesium niobate lead titanate as the piezoelectric because it has one of the largest known piezoelectric coefficients, the D33 coefficient. As the piezoresistor, we use samarium selenide, which undergoes a continuous insulator to metal phase transition as a result of applied pressure. And we were able to demonstrate, and this is our first real measurements, that you can actually make functioning transistors this way. They are by no means optimized, but I think this does show a platform for potentially substantially reducing the power required to run a transistor while simultaneously increasing its clock frequency. And in the interest of time, I won't walk through how we made those devices, but I will simply give you some conclusions so that you have time for some questions. Hopefully what I've shown you in this short talk is that sometimes if you understand the fundamentals of where domains are in ferroelectric thin films, you can use this to increase the figure of merit of that device. And the specific example I showed was the case of the energy harvesting figure of merit. I also demonstrated that the ability to integrate electronics on actuator arrays offers the possibility of doing low wire count devices for a large number of applications, including the proposed LINX X-ray space telescope. And my last topics were on piezoelectric micromachined ultrasound transducers, which we've demonstrated over quite a wide frequency range, and also the piezoelectronic transistor, in which the piezoelectric itself becomes the computation element. So with that, I will stop and take any questions any of you might have. Thank you for your attention. So are there any questions? Feel free to unmute or ask your question by chat if that would be helpful.
Dr. McKinstry, this is George. Can you hear me?
Yes, I can hear you.
So, very good talk. Thank you. Some of those devices you make are impressive. How, I guess, out of curiosity, how long does it take to develop some of these devices? So a lot of material science researchers work on for a long time just to get a single layer.
That's a beautiful question. So practically, we've been working on lead zirconate titanate films and how do you optimize the property of those films now for almost 25 years. And so some of my new students don't have to come in and kind of reinvent that base technology, which is why they're able to move it forward to make devices. When we are starting brand new device fabrication, the first thing we try and figure out is literally what order of the steps are we going to do. And it normally takes a student kind of 6 months at least to learn how to do all the steps. And not uncommonly, the first device run of any device might take several months to complete. As we get better and we kind of figure out where the bugs in our processing are, how long it takes to do a device run will depend on how many layers and how many patterning steps. So for the adjustable optics, just to get the piezoelectric on currently takes us a couple of weeks because of the low slumping temperature of the glass. If that were a conventional piezoelectric on silicon, it would take us a day to do that, and then maybe an additional week to do the rest of the patterning. For the micromachined ultrasound transducers, that's usually at least a month-long fab process.
All right, thank you.
You're welcome. And I should say the first fab run never works. You use that one to figure out where the warts are. So it's usually several before we have devices we can show in public. Okay, Sadie, I don't see any other questions. I'm pretty easy to find by email. So if any of you have questions later on, feel free to pop me in an email and I will try and answer, but we can probably go ahead and stop the recording at this point. And I will thank everyone again for their kind attention.
Thank you, Dr. McKinstry.
Bye-bye.
Bye.